What is an imaginary number? An imaginary number is a complex number that can be written as a real number multiplied by the imaginary unit I, which is defined by its property I squared equals minus 1. An imaginary number bi can be added to a real number a to form a complex number of the form a plus bi, where the real numbers a and b are called, respectively, the real part and the imaginary part of a complex number. Now, these complex numbers are used in many fields such as engineering, physics, chemistry, biology, economics, electrical engineering, mathematics, and statistics. Soon, me and my fellow companions will explain some of these fields more in depth.
Okay, now I'll give you a more specific example about how we can use the imaginary numbers in real life, but first I have to explain you what is a phasor. A phasor in physics and engineering is a complex number representing a sinusoidal function whose amplitude, angular frequency, and initial phase are time invariant. It is related to a more general concept called analytic representation, which decomposes a sinusoid into a product of a complex constant and a factor that encapsulates the frequency and time dependence. The complex constant, which encapsulates amplitude and phase dependence, is known as phasor complex amplitude and tenor or even complex OR. Now that we know what is a phasor, we can understand how does the circuits work and how they use an imaginary number. In circuits and everything that has to be with them as transformers are of a great help. The imaginary numbers in the moment that you are working with inductances and capacitors, because the most used alternative source are the sinusoids and the functions of the capacitors and inductors can be modulated in a phasorial way. This means that you have to work with the domain of time and you have to work with the domain of frequency.
Imaginary numbers are often used in applied maths and physics. Complex numbers occur quite naturally in the study of quantum physics. They are useful for modeling periodic motions, such as water or light waves, as well as alternating currents. Understanding complex analysis, the study of functions of complex variables, has enabled mathematicians to solve fluid dynamic problems, particularly for largely two-dimensional problems where viscous effects are small. You can also understand their instability and progress of turbulence. All of the above are relevant in the real world as they give insight into how to pump oil in oil rigs, how earthquakes shake buildings, and how electronic devices work on a quantum level.
Now, I'm going to explain with more detail how can we apply the imaginary numbers in electricity. Imaginary numbers are not imaginary. They just do not belong with the group of numbers that we named the real number set. When electricity flows through an electrical circuit component like a light bulb that resists the flow of electricity by using some of it to do work, the current flowing through the bulb is purely real and can be measured by a current meter accurately. When electricity flows through other devices where no real current can go, the current flowing through that device is purely imaginary. If it were measured, the current flow through the device would show 0 because a meter can only measure the real part of the current. Think of it like this. A coil is just a wire. So if you run electricity through it, there is no real voltage drop because there is not real resistance. A capacitor is just two pieces of metal that do not touch. So, if you put a voltage through it, no real current can flow. It's why they use imaginary numbers in electricity. Also, as brain waves are oscillating electrical voltage in the brain, measuring just a few millionths of a volt, they use imaginary numbers too. So, imaginary numbers can be applied in biology and a lot of sciences.